Today we're going to be talking about how to find the point on the cone, which is closest to the given point. And in this particular problem, we've been given the equation of the cone, which is z squared is equal to x squared plus y squared, and a coordinate point 4, 2, 0. And we want to find the point which lies on this cone's surface, which is closest to the point 4, 2, 0. Now we should recognize this as a multivariable applied optimization problem. And for that reason, we know we're going to need at least one other equation. Keep in mind that we're trying to minimize the distance between the point on this cone and this given coordinate point, right? We're trying to find the point on the cone which is closest to the given point. That means essentially that we're looking to find the smallest possible distance between this coordinate point and the surface of the cone. So since we need to find the smallest possible distance, that means we're going to need to optimize or minimize the distance formula in 3 variables. So remember, our distance formula in 3 variables is the following. We say d is distance, and it's equal to the square root of quantity x minus x sub 1 squared plus y minus y sub 1 squared plus quantity z minus z sub 1 squared, and we take the square root of that whole thing. That's the distance formula. This is the formula that will give us the distance between 2 coordinate points in 3-dimensional space. Well, here we have one coordinate point, 4, 2, 0. We can plug that in for x sub 1, y sub 1, and z sub 1. But because we're going to try to minimize this distance formula, we know that not only are we going to need to do that, but we're also going to need to eliminate a third variable. We can't optimize this equation if we have 3 variables involved. So we're going to try to eliminate our variable z, leaving us only with the variables x and y. That'll give us a function in 2 variables that we can more easily optimize. So here's what that's going to look like. First, we're going to plug in 4, 2, 0, and we're going to get d is equal to square root. Here we're going to get x minus 4 squared. So we'll just say x minus 4 squared plus y minus 2 squared when we plug in the y value from the coordinate point, plus z minus 0 squared, which is essentially just plus z squared. Now notice here we have a value for z squared with our other equation, which is the equation of the cone. What we want to do is plug in or substitute x squared plus y squared in here for z squared to put this equation for distance in terms of 2 variables only, x and y. So distance now is going to be square root of x minus 4 quantity squared plus y minus 2 quantity squared plus, and here's where we make our substitution, x squared plus y squared in for z squared. Now this is the equation that we want to optimize, but before we go ahead and take partial derivatives, let's try to simplify this equation somewhat. We've got this square root over here on the right-hand side. Things would be a lot simpler if we didn't have this square root. We can go ahead and square both sides without changing the equation. That'll give us d squared over on the left. Our square root sign will drop away on the right, and we'll be left with quantity x minus 4 squared plus quantity y minus 2 squared plus x squared plus y squared. We can also go ahead and expand these x minus 4 quantity squared and y minus 2 quantity squared terms and simplify our equation that way. So when we do that, we'll get x squared minus 8x plus 16, we're just foiling this out here, plus y squared minus 4y plus 4, and then we have plus x squared plus y squared, like this. When we simplify here, we have x squared plus x squared. That's going to give us a 2x squared for these 2 terms. We have a negative 8x, so minus 8x. Then for our y terms, we have plus y squared and plus y squared, so let's do a plus 2y squared here. Then we have a minus 4y, so that takes care of that term. Then we have a plus 16 and a plus 4, so a plus 20. That's going to be equal to, of course, d squared. Now it doesn't really matter that we have d squared here, because since we have d squared and this right side of the equation, we squared both sides, we haven't really changed the equation at all. This is still the equation that we're trying to optimize. So in order to optimize now, we want to take partial derivatives of this equation. So let's go ahead and say the partial derivative of d squared with respect to x is going to give us here 4x minus 8, and all the other terms, 2y squared minus 4y plus 20, drop away because there's no x variables involved. if we take the partial derivative of our equation d squared with respect to y, we're going to get 4y minus 4. All the other terms drop away because there's no y variable involved. Now remember that the point of finding partial derivatives is to set both of these partial derivative equations equal to 0 so that we can find a critical point. So here, if we set this equal to 0, we add 8 to both sides, we get 4x equals 8, or just x equals 2. Same thing over here, we set this equal to 0, add 4 to both sides, and we get 4y equals 4, or y equals 1. Since we only have one x value and one y value, this tells us that there's only one critical point, which is the point 2, 1. In order to find the coordinate point that lies on the surface of the cone, which is closest to 4, 2, 0, we just plug this critical point 2, 1 into our equation here for z squared to find a value for z. So what we're going to get here then is z squared is equal to, plug in 2 for x, 2 squared is 4, plug in 1 for y, 1 squared is 1, so we get 4 plus 1, or z squared is equal to 5, or z is equal to positive or negative square root 5. That tells us that we actually have 2 points that lie on the surface of the cone that are equidistant from our given coordinate point, and those are 2, 1, positive square root 5, and 2, 1, negative square root 5, or if we list the points together, 2, 1, positive, negative root 5. So these are our two answers here. If we want to use the second derivative test to verify that this critical point represents the shortest distance between the given coordinate point and the surface of our cone, all we need to do is find second order partial derivatives. So we have our first order partial derivative with respect to x here, we got 4x minus 8. If we find our second order partial derivative with respect to x, we just take the derivative of 4x minus 8 with respect to x, that gives us 4. The second order partial derivative with respect to y, we're going to take the partial derivative of 4y minus 4 with respect to y, that's going to give us 4. And the mixed second order partial derivative, we can start with our first order partial derivative for x, take the partial derivative with respect to y, but of course that's 0 because there's no y variable involved in 4x minus 8, so we get 0. We evaluate these three values at our coordinate point 2, 1. Well, of course, there's no variables to plug in for, so we don't really have to evaluate it 2, 1. We just have to plug these values into our second derivative test. And remember, the second derivative test, we always use notation d. That's a little confusing because we used capital D for distance. So instead, let's say just second derivative test is going to be equal to, remember here we take the second order partial derivative with respect to x, which is 4. We multiply it by the second order partial derivative with respect to y, which is 4. And then we subtract the mixed second order partial derivative squared. So we square that value and subtract it from the product of second order partial derivatives with respect to x and y. So when we simplify here, you can see that we just get a value of 16, which is greater than 0. Because the second derivative test gives us a value that's greater than 0, we have to go look at the second order partial derivative with respect to x. This value is also greater than 0. So because these two are greater than 0, that tells us that the critical point 2, 1 is a minimum, which proves that we've minimized the distance between this given coordinate point and the surface of the cone, and 2, 1, positive, negative square root of 5 represent 2 points on the surface of the cone, which are closest to the given coordinate point 4, 2, 0.